Welcome to the second SEG Virtual Student Conference. This event is organized by members of the Europe Regional Advisory Committee of the Society of Exploration Geophysicists. I'm Aurélien Röser and I'm one of your hosts today. Today we will witness 10 students from various European universities presenting their research, giving us insight in the latest results. The event is divided into 3 sessions, and total we have 10 presentations, and in between each session we will have a 5-minute break. Each talk will be roughly 10 minutes, after which you will have the option to either ask a question or post a comment. For this you have 2 options. You can either use the Q&A Zoom option section here, or if you're brave enough, you can virtually raise your hand and then we can grant you permission to unmute yourself. And if you decide to do so, please shortly introduce yourself. Please note that this event will be recorded and later posted on the SEG website and on the SEG YouTube channel. Now, without further ado, I would like to pass the torch to our first 2 session chairs, Tatjana and Elisabeth, who will chair the session with 3 interesting talks about electromagnetics.
Hello, everyone. I welcome you to our today's student conference. Our first speaker is Luigi Bianco from University of Naples, Federico II, and he will talk to us about magnetic modeling in the ancient Abbey of San Pietro in Crapola, Napoli, Italy.
Hi, everyone. I'm Luigi. Okay. How can I share the video? Yeah. Share. I will present. I'm pleased to be here with every one of you. I will present a magnetic modeling of in the Abbey of San Pietro in Crapola. That is a site of archaeological interest. The survey is a part of a large collaboration between 2 departments of the University of Naples Federico II and the Town Council of Massalubrense to perform a scientific study for the first time in this area. The area is famous all over the world as Crapola's Fjord and is in town of Massalubrense in the state of Naples in southern Italy. The site is known to represent the location of a medieval abbey named San Peter in Crapola. Only a minor recent chapel and a couple of columns on the ground witness the presence of the old structures. By ground survey and architectural reconstructions, it is possible to speculate the presence of an abbey, its church, and a buried crypt. It is an articulated area of the southern Apennines, also called Lattari mountain chain. The rocks forming this chain are basically limestone from Cretaceous, here, overlaid by Miocenic sandstones, and everything is covered by tuff and pyroclastics from Campi Flegrei and Vesuvius. The area was divided into 4 grids. We will discuss the two major, and we will refer to grid number 1 as Abbey side and grid number 4 as a church side, following the old structures which should be buried on each side. Grid Abbey side is 16 per 7.8 meters, while grid church side is 13.5 per 8 meters. The interprofile step is constant and is equal to 0.5 meters. The survey consists in measurements of the vertical gradient of magnetic field with a magnetometer in radiometric array and a GPS survey using an antenna with the central frequency of 400 megahertz. We will clearly focus on the magnetic data. After a deep analysis of the raw data, a filtering was deemed necessary to deal with the hidden error along the direction of acquisition, particularly present here, as you can note. A discrete wavelet transform was so performed with an interpolating wavelet along x direction, where the heading error was stronger, and then shift twice. Also on the grid AB side, a wavelet transform had been performed, here with a triangle wavelet along the x direction, and here shift only once. So then the filtered maps were then interpreted using two different methods proposed by Fedi for depth estimation and the structural index definition. The first method is the so-called multi-ridge analysis proposed by Fedi in 2009. A multi-scale dataset is built up by upward continuation of a potential field or its vertical derivatives. On this dataset, three different types of ridge are defined as the zero of the first horizontal derivative, the zero of the first vertical derivative, and the zeros of the field itself. Then the depth is estimated by the graphic intersection of these three families of ridges. A second method is the depth from extrema points, better known as DXP. A multiscale is built up as before. Then the dataset is scaled using specific laws which accounts for homogeneity degree of the source. The depth is determined by searching for extrema points of the scaled field. On the map of the church side, three principal anomalies were identified. On the anomaly number 2, both the interpretation methods were performed for a depth estimation. So here we can see that the top of to the top was estimated by both methods at 0.5 meters from the surface, and a structural index of 2 had been estimated, suggesting a possible horizontal body to be present at this depth. As modelized from magnetic data and compared with radar data, it's clear that all anomalies have a top at 50 to 70 centimeters under the surface and extend downwards until at least 1.2 meters. The number 2 and 3 anomalies are interpreted to be walls of the ancient church made by different materials, while the number 1, not completely solved in the magnetic data, but better imaged by radar, should represent the vault of the crypt. Here, better imaged. On the map of the B-side, different anomalies were identified. On the anomaly number 1, only the multi-ridge analysis was performed due to short time before excavation took place. These were the other anomalies we identified. Also here, by the intersection of the three family of the ridges, we can see that the top of the source body was estimated to be at 0.8 from the surface. Also here, the structural index we identified should represent an horizontal body buried. By the comparison also here from of the magnetic data modeling and radar data, the anomalies were interpreted to represent the walls of the ancient abbey, with a depth top, as we stated before, about 70 to 80 centimeters. While modeling continued, depth estimation for this area were reported to the archaeologists, and the anomaly number 1 was chosen for an archaeological test. Archaeologists found a wall in limestone bricks here with a depth top of 70 centimeters, so perfectly matching what were our modeling and depth estimation, and also the structural index were very good identified. Here we can see how the test found a wall that perfectly matched our anomalies in the mag and radar data. The final remarks are that we provided the important guidelines for archaeological excavation, minimizing the impact of digging in a protected marine park. The successful excavation validates the results for the church side that will be very useful for future archaeological excavation already in program, maybe in the next years, because of COVID-19 pandemic spreading this summer. Interpretation methods proposed by FEDI have been proved to be effective in archaeological contexts, and there are strong evidence for scientific community, of the role of multi-methodological geophysical surveys and the importance to have tested tools for data filtering and modeling. I really want to thank you for your interest. And please, your questions are really welcome for me.
Thank you very much, Luigi, for this interesting presentation on the practice of magnetometrics and GPR for archaeological survey. Are there any questions from the audience? I don't see anything at the Q&A. I will start by asking you how old is the ancient abbey, because I don't remember if you talked about it.
The first estimation were about the first century of the first millennium, so 1100 or something like that. So early medieval time, yes.
Was it, you said the third layer over the sandstone was tuff, volcanic tuff. Do we know if any of these covers were produced after the abbey was built?
Yes, they were all autochthonous materials, as this study also comprised the support of geologists, petrographics, and so they stated that these were bricks made all by autochthonous materials. So the limestone we can see here also in this picture, or tuff that is practical in almost everywhere in this area. Yeah.
We have one question from Zahim Ibrahim. He asks which correction factor and filter tool was used for this analysis.
Okay, so the filter tool is a tool that we use in our university for wavelet filtering. The correction factor is, I cannot answer this correction factor. We used a wavelet with the parameters I showed you in the slide. Yeah, maybe I can go back. And that we thought that were the best for each case. In church side, we used an interpolating wavelet along this direction where the hidden error is present. You can see very well here that then is not anymore present in the filtered map. And then shift along X and Y this wavelet for twice. For this other side, for this other grid, we choose to change the wavelet shape, because it performed better on this grid, a triangle wavelet. And we shift only once because the results we were satisfying.
Thank you. Next question by Infinix is why was the magnetic method chosen over the geoelectric one? which is thought to be more effective in such excavations.
Yes, so the magnetic data here was used because, as you can see, the area is not easily reachable. So, and then here you can see that it is very tiny, but it's covered by vegetations and other stuffs, and were really, really difficult to use geoelectrics here. While here is a pavements. So how to perform geoelectrics here? Battery, radar, or magnetic data. These are something like that 700 steps. So really better also to transport a magnetometer that the old instrumentation for geoelectrics.
Yeah, this is understandable. Any more questions? I will ask one last one. You said you have in plan to do this combined methodology for other archaeological sites, and I would like to ask you what you have in mind.
This project should last for other years, but probably the geophysical support will be these, and the archaeologists will choose other area we analyzed. Some probably the ones from the church side here to perform a focused digging. To find some witness that there is that there was a church here.
All right, thank you. So you will continue your focus on this area.
Thank you very much.
Yeah. I don't know if will we continue now? Yes, it's almost time. So yes, thank you very much for
I stop
your
share,
talk.
Yeah.
Yeah.
Okay.
Thank you.
Thank you, you too.
Okay, thank you to Luigi Bianco for your presentation. So now we can continue to the next presentation. Is going to be by Ivan Perepletkin from Industrial University of Tumen. His presentation is about complex integration of electromagnetic methods to refine the near-surface geological model in Russian Arctic.
Good morning, good afternoon, everyone. Can you hear me?
Yes, we can hear you.
All right, so let me start with the demonstration of my screen. Can you see everything clearly?
Yes, we can see it.
All right, so let me start. My name is Ivan Perepletkin. I'm fourth year student of the Industrial University of Tumen, Russia. And I would like you to tell about my scientific topic as complex integration of electromagnetic methods to refine the near-surface geological model in the Russian Arctic, which I have completed with my scientific supervisors, the specialists of the Novatech Scientific Research Center, Doctor of Science Vladislav Kuznetsov and Yuri Dolgih. So to introduce my topic, I would like to tell you about the actuality of my this particular scientific article. The geophysical exploration in Russian Arctic in general is really complicated, but is going to be much more actual because the more and more hydrocarbons deposits are developing in this area. In spite of the harsh climate, we used to deal with different different technical problems, like during the processing and the interpretation process, So first, it's about the low velocity zone and the complicated part of low velocity zone in the permafrost, because it's can divide it not only by the permafrost, but also consists traps and carbonates. Besides that, there are different vertically and horizontally complicated near surface zone structure. And one more really important factor is ecology. So right now, we didn't have any generally accepted technology for travel time data inversion, which can guarantee 100% correct forecast of the depth velocity model, just in case to make further kinematic amendments correct, and static amendments too. So here you can see just an overview slide. You can see that permafrost covers more than 50% of Russian territory. So just a quick question to the moderator, can you see my mouse?
Yes, it's clear, we can see it.
Yeah. So here you can see our objects of study and what ways can we use. So first, there are lots of technologies were developed by Russian and foreign scientists for studying the permafrost zone and low velocity zone. Of course, first there are seismic methods like microseismic logging data, or even this innovative technology like multi-component seismic or multi-level seismic. Here is just an overview information. Yes, the seismic data can solve the problem, can identify all local zones clearly just to make further amendments correct. But on the other hand, it has two main disadvantages, like high price, and another disadvantage is really actual for Russia nowadays. In the majority of situations, we still use explosive sources instead of vibrators. So the alternative one technology is electromagnetic methods complexing. It has the same good result, but first, it's environmentally friendly technology and given even more vertical and horizontal resolution with providing straight saturation forecast. Yes, sometimes it takes much more time for processing and interpretation, but currently by Novosibirsk scientists, two programs were developed by introduction with complex with seismic. So the first method is transient electromagnetic sounding. It's subsurface type. It's really this method has like really easy physical principle based on transient electromagnetic field. Its main advantage is that it provides high horizontal resolution with providing direct saturation forecast based on, so we can identify at the same time the lithology, and also it can be easily recalculated to the acoustic parameters, like using the Faust equation, and also another one, empirical interconnection, which is especially for the permafrost in Eastern Siberia. This formula have been done experimentally in 2018. So the second one method, it's a unique technology which is just been patented 2 years ago by Russian scientists. It's ultraviband G-radar radiometry on the reflected electromagnetic waves. So as you can see, the wave propagation picture, it has a really similar principle like the seismic technology. And also like the simple G-radar, but the only one difference, so the main advantage is working at really high operating depth because of first lack of signal gating, while realizing secondly because of the powerful source, and thirdly about special using antennas. So here you can see just the general scheme of the G-radar equipment and the methodics and techniques of the field work. So using the Wi-Fi generator, it can be further proceeded in the field conditions. So what became the assumption of our study? Our colleagues from Timer LLC combined the complex research in the Yamal Peninsula in the unique engineering geological objects So you can see the correlation between the GPR data and the STM data, the transit electromagnetic data. So 3 layers were identified by low velocity zone, another one by the permafrost zone, and the conductive layer. And so if you can see here, the GPR data correlates with the pulses of GPR correlates with the boundaries and can identify like local lithological borders which cannot be identified by seismic or STM data. So here's the slide, another one slide, our results in 2018, which we have done in the Western Siberia. So we can see that it's a satisfactory resolution and the correlation with another one lithological factor, the well logging data. Some relic permafrost layers were identified clearly, and here's the example from our colleagues from Irkutsk. So you can see that how good how much better the quality is by the electromagnetic data in comparison with the seismic one in the low velocity zone. But still we have like really poor vertical resolution without complexing with the georadar technology. I'll describe why. So we can see just like averaged calculated per each layer. So. And finally, in November 2019, in Taimyr Peninsula, we realized 2 methods in the complex. So you can see that how much qualitatively and quantitatively the low velocity zone was identified according to these geological sections. So here is correlated to the trap zone. You can still see that according to the STM geoelectric profile, we have like average calculated average calculated value of electric resistivity. So here, according to the radiogram, you can see that it's in nanoseconds instead of milliseconds, like in similar seismic. And it's in spite of vertical resolution, good vertical and horizontal resolution, it still has satisfactory quality up to the depth to 150, 160 meters. So in comparison to like simple georadar, it's much more, it's like really progress. So, and another one good example, which were done in this close to the previous area, it's complexing GPR with seismic, because technically these methods are not used in complex really often. But by the progress with the depth increasing, we can see the same situation, that you can see the following situation, that the georadar technology can help identifying like overlapping horizons, which cannot be clearly done by seismic because of the trap rocks in the Eastern Siberia. So because of this low resolution and low quality of low velocity zone, it used to be really hard to make further data processing. But according to the georadar, we solved this problem and identified this horizon. So speaking about the general conclusions, the combination of these 2 methods allows implementing seismic data in the near surface zone. And of course, it provides like much more quantitative and qualitative results, and spreads the amount of tasks, and also it's also all electromagnetic technologies are economically justified, because the complex work costs just 75% of 2-dimensional seismic per this same area in kilometers, and so, and also can be actual during the parallel engineering solution by the all stages of exploration and further exploitation and development of particular oil deposit. So thank you so much for your attention. You can ask me, feel free to ask me any questions. I will appreciate it.
Thank you so much for your presentation. Okay, now, so we are going to go to your questions from the audience. So here there is one. It says, how did you integrate the GPR and STEM dataset for the final model? Just by comparing, overlaying, especially in your first example.
So first example, you mean this one, right? Yeah, if it's about
yes,
this example,
it's that
yes,
one.
yes. So it's by comparing because I'll explain. So let me just make it to the full screen. It will be better. So the first, the STM data was realized, and just 2 months later, the first time was experimentally realized the georadar data. Yes, it's just like comparing, because even you can see that we use different software. Here's the special Russian software based on like classic interpretation of electric method. Here we used the integrated software product of REFRA. So, any other questions?
Yes, here we have more other question. And in complex seismic and GPR slide, are we able to map beneath the basalt zone?
Could you repeat, please?
Yeah. Are we able to map beneath the basalt zone?
So if you about the structure map, yes, we can. Because this method, it's like so the GPR technology is being realized like not a direct method. It's just in case to simplify further further mapping of by the seismic after the interpretation of seismic data in this particular region. It's just made for simplification and of the static amendments correctment. Yeah.
Okay, and now the last, well, one question more. Have you tested the GPR on unfrozen ground? And if so, what depths of penetration can you achieve?
Yes, thank you for this interesting question. So I'll begin about particular my presentation. The result in the permafrost zone were made just because of the lackage of data in seismic. So yes, of course, the GPR method, the GROT ultra-wideband GPR method of the on the electromagnetic on the reflected electromagnetic wave, sorry, was developed in 2013 to 2017 and was tested in the province of Queensland, Australia, and also in the Alps. So speaking about Europe, so in different conditions. The maximum depth which was conducted was around 400 meters in Australia, and the lowest one near Moscow, it used to be like just first meters because of really of specific combination of rocks in the low velocity zone. Because the main disadvantage of the method, I just want to manage about this question. The disadvantage that it has low resolution in such type of water saturated rocks. If it is not very big water saturation, so it has much more good quality. For example, in permafrost and trap zones, as I showed you before.
Thank you, Ivan. Now we will move on to our next speaker, who is Filippo Accomando from University of Naples, Federico II, who will talk to us about a preliminary study for the development of an airborne magnetometric system with applications to the archaeological area of Vulci. Thank you.
Thank you. Good afternoon to everyone. I'm sharing my screen now. Okay. Okay. In this work, I will present a preliminary study for the development of an airborne magnetometric system and some tests using new magnetic acquisition technologies. This work derived from the opportunity to have the MFAM geometric magnetometer, which is the result of recent research in the field of instrument miniaturization. In fact, this new magnetometer, compared with others, has a lower weight and volume, a similar sensitivity, but a higher sampling frequency. This specification makes it suitable for drone investigation. In our configuration, the development board, the sensor driver electronics were placed in a rigid plastic box. The flex cables are passed through a high-density polyethylene tube and are connected to the sensor, which are also contained in a smaller plastic box. The sensors have the same configuration shown in Figure B and are held still thanks to an expanded polyethylene structure. The distance between the center is about 2.5 centimeters. Today, WAV systems are new technologies and are used in many contexts. For example, in agriculture, in critical situations. Obviously, they are also used in geoscience. A lot of geophysical sensors can be hugged under drones. The advantages are to be an autonomous platform, decrease field time, survey difficult to access displays, decrease risk to field personnel. And in particular, this system allows a higher rate of coverage than terrestrial magnetic survey and a higher resolution than manned airborne survey. So the goal of this study are to evaluate the MFAM magnetometer and compare it to other instruments used for the first time. The MFAM magnetometer for ground magnetic survey investigate the magnetic recorded signal in order to optimize the survey and design, evaluate the WAV generating magnetic field and strategy to minimize the impact on the magnetometer sensor, test for the first time in Italy a prototype WAV magnetometer system with the MFAM magnetometer, acquisition, processing, and interpretation of magnetic data acquired using the MFAM magnetometer over an area in the archaeological site of Vulci in order to obtain useful results to define excavation area. Part of this work tries to understand more on magnetic static and dynamic effects to WAV platform. In order to calculate the effect due to the aircraft components, two tests were performed. The MFAM magnetometer was transported to an area of 30 centimeters from the drone for the first test and 80 centimeters for the second test. During both tests, the WAV was turned off. This test demonstrates that the drone is made of materials which are susceptible and create a change in the surrounding magnetic field. So total field in figure A and B were upward continuated. Using a distance of about 1.5 meters from the drone, the magnetic effect should be sufficiently well attenuated. To evaluate the full magnetic effect of the WAV, two sets of observations were carried out. Once without the WAV and once with the WAV and its engines running. Obviously, the rotors should spin with their full speed to measure the maximum magnetic signature of the WAV. This was not possible for safety reasons, so that the engines were powered to about half their power. By subtracting the magnetic field measured in these two conditions, we could have an estimate of the magnetic noise. Field associated to the WAV and its engine in motion is rather complex in shape and rather strong in amplitude. To simulate more realistic flight conditions, these data were upward continuated to a set of distance from 10 to 150 centimeters. And from this test, it appears that a distance of about about 1.5 meters from the drone, the magnetic effect should be sufficiently well attenuated. Thus, this experiment was important to define a minimum distance to be used in test flight. Then previous tests have helped us to understand how far to keep the magnetometer to avoid interference with the drone. So the next step is testing for the first time in Italy a drone magnetometric system using FAM. The FAM was suspended 1.5 meter below the WAV at an elevation of 10 meters. 9 survey lines of 60 meters were planned and flown with a line spacing of 5 meters with a speed of 5-10 meters per second. The data sampling rate was set up to 1000 Hz. Figure A shows only the data recorded during the flight. From the figure, each line flown in one direction is an average level different from that flowing in the other direction. In addition, there is a strong noise associated with the observation collected at the start and at the end of each survey line due to the swinging of the sensor during the flight. Therefore, to improve the data quality, all the data collected in the first and the last 5 meters for each survey line were removed and the average value of each acquisition line was subtracted. The map shows the maximum and the minimum value are restricted in a narrow range, but there is only a small trend because the survey area presents no particular shallow magnetic source. And the map presents also some periodic feature which could be still associated to the oscillation of the sensor at the beginning and at the end of each line. Here, from the top to the bottom, the data recording during the flight and the pitch roll AF angles. These angles correlate well with the turning of the drone. Furthermore, this information could help filter noise related to the swinging of the sensor. After this test, we used the FAM for an archaeological investigation. So, in the archaeological site of Vulci, 2 ground magnetic surveys were executed using FAM magnetometer. The first survey includes the second one that represents the tail of the first. Then data from the first test was compared with data acquired in a third survey carried out with potassium magnetometer. The goal is to find a tomb with a barrel shape typical of this area. Vulci is part of the Volsino volcanic district, and the magnetic survey area is located above a few decimeters of plate surface sediment which cover an 8-meter travertine bank. This means that despite the volcanic nature of the substrate, the expected magnetic signal should be quite undisturbed. To my knowledge, this is the first time that FAM magnetometer has been used for a ground investigation. So the result and the measurement add value to this research. The vertical gradient maps show a very similar pattern, and the main anomaly indicated with the red circle can be recognized in both datasets and could be a tomb. So the tail was made using less spacing between the acquisition profile. So I made the vertical gradient and the analytic signal to better see the anomaly. So I tested the geometry of a typical Etruscan tomb similar to others found in this area. Size, depth, and the magnetization of the synthetic source are shown, and I computed the vertical gradient and the amplitude of the analytic signal observed at an altitude of 1.20 meters. One of the main objectives of this study is to understand the possible problem of the development and use of magnetometric airborne system. As possible application of the WAV includes the archaeological one. So computed the vertical gradient of the synthetic model at different altitudes, simulating different WAV flight altitude. The vertical gradient displays well the anomaly up to 3 meters of altitude, corresponding to an WAV flying at 4.5 meters. In fact, at this altitude, the anomaly amplitude is still greater than 10 nanotesla per meter, typical of the archaeological area. These flying altitudes should be frequently possible in archaeological sites, even in presence of small obstacles. So we can conclude that FAM and vapor potassium magnetometer. Sorry,
continue.
So the FAM are quite valid data in our prototype configuration. FAM are much easier, comfortable to use in field operation and accessible for one platform. Static and dynamic effects of the drone are well attenuated at a distance of about 1.5 meters. A first to have survey tests show a number of problems to address in the future. The main of these being the excessive oscillation of the sensor at the beginning and at the end of each line, producing periodic feature in the measured field. The Vulci survey allows to highlight the show wavelength magnetic anomaly that could be associated with an Etruscan tomb. In this case, a WAV survey could be able to detect the associated signal if the magnetometer is kept at an altitude non higher than 3.5 meters from the ground. Thanks for the attention.
Thank you very much, Filippo, for the talk. Now, do we have any questions?
I have a problem. Okay.
So the first question from the audience comes from Valeria Caprioli. She asks, how did you hang the magnetometer right off the drone?
Yeah, FAM was suspended 1.5 meters below the drone and was anchored to 4 drone arms with ropes intershaped with a plastic tube to cushion the takeoff and ending phase time.
Thank you. Any other questions? Yes. Last one from Xinseng Den. The UAV height is the same above the ground for the UAV magnetic system, and how to cancel the height effect for the magnetic sensor.
So I showed before. In this part of my work, I show how the signal is attenuated at this distance. So 1.5 meter is the right distance from the drone to attenuate the noise due to the aircraft components and from engines. And obviously I use in future I hope to do more tests using the maximum power of the engines. So maybe we can change the distance from the drone.
Thank you very much. Now the first session is over. We will take a quick 5 minutes break till 5 minutes to 3 Central European Standard Time. And then we will continue to our next session on mineral exploration, where chairs will be Florencia and Jono.
Okay, hello everyone. I guess it's time for the second session on mineral exploration. Our first speaker is Diego Delgado Yanes from Uppsala University, and he'll talk about confluence tailings in Chile.
Good afternoon. For some of you, good morning. I'm going to talk about my bachelor thesis related to tailing characterization and special focus on both economic and environmental relevant metals. So as general context, geoscientists now will have more challenges as society is basically demanding for more type of raw materials, particularly metals, but also the total amount is increasing. So some challenges are how to source society, how to do it in a sustainable, ethical way, but also where. So we need to go for exploration in both greenfield or brownfield, or also looking for secondary sources as tailings. If you are not familiar with the concept, we can discuss it later. So most of these metals are considered critical by the European Union. You have the list here, and we focus on a zinc mine in Chile. Zinc is not part of this critical list, but is it coupled with both germanium and indium. So as I told you, the main objective here was to characterize these tailings, focusing on what is interesting from the economic and environmental points of view. El Toqui mine is located in the region of Aysén, my region in the Chilean Patagonia, and this is just to show you the methods we use in this work. El Toqui is a manto-type skarn. It's a polymetallic one. The main metal is zinc, but there are also other commodities, as you see. The main metallic mineralogy is sphalerite, and here you can see that there are different type of alterations, all related to skarn types. And as I told you, the main mineralization is sphalerite. Okay, so basically I took samples from 2 different drill cores separated by 200 meters. Ideally, I took 1 sample per meter, but that's ideally. Regarding the macroscopic description, we couldn't see that much, to be honest. Just some quartz, magnetite, amphiboles, but doing more detailed mineralogical analysis, XRD in this case, we can see that the main phases are silicates as actinolite, chloride, quartz, some pyroxenes and others, and some sulfite as sphalerite, pyrite, and pyrrhotite. This is really interesting and relevant for what I'm going to show you later. So I considered the diffractograms patterns, and I could notice that there are some similar patterns in depth. So I could divide every drill core in 3 sections that I called alpha, beta, and gamma. Also, I separated Europe fraction. Chloride here is the main clay. I used different type of ponderation of estimations of this proportion, but also we can discuss that later. Regarding geochemistry, we have that the elements here are more or less coherent compared to what we expected according to mineralogy. The first segment, the shallowest one of the first drill core shows, for example, below 1% of zinc and arsenic with maximum of 2.25 and around 1%. There are also interesting traces of tungsten here, but probably this is derived from the samples preparation. Here you can see at the right that some elements of copper, zinc, lead are especially correlated, and we also corroborate that with Pearson matrices of correlation, of course. The second segment showed an increasing amount of zinc, above 1%, and also same with arsenic, and some interesting traces, hundreds of ppm of copper and lead, and again the same correlation here. Finally, the deepest zone shows really small amounts of zinc compared to the other sections. For this second drill core RaO2A, we have more or less the same metals, or elements. I consider correlations above, in absolute value, I mean above 0.75 as really high correlation, which I highlighted in green here. Okay, the first segment of this second drill core exhibit again, less than 1% of zinc and arsenic with maximum peaks of around 1%. There's a lot of copper here and also some tungsten, but we have this issue with contamination that I mentioned before. The second segment shows an average of 1% of zinc with a peak of 1.65, sorry, and again, thousands of ppms of lead and also copper. The final segment here is showing again this decreasing amount of zinc, just some hundred of ppms. Regarding the grain size granulometry, I separate the fractions of each sample in sands, silts, and clays to do an analog as these soil classification diagrams, just to show you that in general, the first drill core is coarser than the second one. And we also consider some metallurgical parameters as D10, D30, and D60 to understand if it's possible to reprocess this material or not. Comparing geochemistry and mineralogy, we have that everything is more or less coherent. It's not totally clear here what's going on with the cobalt, which is a really important metal nowadays. If we compare both drill cores, we see that they exhibit the same characteristics in depth. So we can say that both are analog, which is not totally obvious at the beginning. And another fact that the deeper levels are in general finer and show low concentration of iron, for example. So some observational recommendations after the results I show you. We can use sequential extractions to understand where are the most important metals hosted, because in the case of zinc, not necessarily is just included in sphalerite, as there are some secondary processes as oxidation and remobilization. Other studies say that these tailings are contaminating the area. The geologists there say that that's impossible, but most likely it is, and it's a source of pollution. What are the most interesting economic metals here? Of course, zinc and some traces of copper and lead, which are concentrated in both middle sections of this drill cores analyzed. According to some previous works, it is possible to extract or reprocess zinc if the initial grades of the tailings are around 2%. And in this particular case, I recommend to pre-concentrate this tailing, as there's a lot of magnetite, which is really easy to separate. Some conclusion of this work, okay, we understand now the main mineralogy, as I told you, some silicates as quartz, caudinites, amphiboles, carbonates in general, and also sulfite as sphalerite, arsenopyrite, pyrite, and pyrrhotite. The main elements are coherent, as I told you, which compared to what we expected. We can consider that both drill cores are analog. In general, tailings are really heterogeneous, so this wasn't that obvious initially. Some metals are probably coming from reagents used in flotation, as some thiophosphates are used, and then that explains the high amounts of phosphorus, for example. The correlation matrices were really helpful to understand the mineralogy from XRD because that's an interpretation. So it's a kind of backup, statistically backup to understand if our interpretation is correct or not. Regarding the geologic fraction, chloride is the main clay. There's an interesting interstratification of biotite chloride also. If we consider from literature what's the granulometer that is suitable for flotation, that is between 45 and 270 tilers. Considering this criterion, we understand that just the first two sections of the first drill core are suitable for reprocessing. From the environmental point of view, zinc and these traces of copper and lead are potentially valuable in the future. And from the environmental point of view, arsenic and some little traces of cadmium. There's a lot of carbonates, so the geologist says that the acid mine drainage is totally neutralized, but probably this neutralization is just partial. Some suggestions: do some column assays in future studies to understand to simulate the condition of these tailings, also do some more accurate mineralogical analysis to understand how are the ores, and also some mitigation is recommended to, as the word said, mitigate the pollution coming from this tailing. Okay, thank you very much for your attention. Now it's time for the questions.
Thank you. Are there any questions?
I'm going to stop sharing my video. Okay.
I personally do have a question for you, Diego. So you were saying you divided the Boerhof in basically 3 sections, if I understood correctly.
Yeah.
And, for the economic interest, did you find that any of these 3 sections would be most interesting to you? Or do you say it didn't really matter which segment we are looking for? All of the segments have economically interesting minerals.
No, the most interesting one, just considering the concentration, is the beta section from 9 to 21 meters. So we have 12 meters separated by 200 meters of a potential economic zone. But then we need to consider the granulometry. So the second drill core is too fine to be reprocessed by, at least by flotation, but maybe some other methods can be used as leaching, for example. But then we need to understand more about the mineralogy.
Okay, thank you. And we also have a question from Alba Gil. He asked, can you explain or say why there are no evidence of lead, zinc, copper, or lead below the 20 meters? As the drill curls show.
That's really interesting because as I show you here, the deeper levels are finer. So there are 2 options. Oh, this layer is impermeable. So if there's a secondary oxidation and secondary remobilization, when the sulfides are decomposed, they are not penetrating this zone. Or another possibility is that this material is forming agglomerates. So when we did the XRF analysis, we are not measuring the total amount of this type of metals. So that maybe explains why there's less content of zinc and other metals.
Any other questions?
Yes, I have a question. So you show that there are presence of interest minerals in an economic perspective, and I wanted to, like you said, that further mineralogic research need to be done, but are there plans for future extractions or future exploitation of the area? Do you know?
Particularly here, not, because unfortunately the owners of the mine are bankrupt. It's a mine from Australia, so we finished these studies and next year they went in bankrupt. So I think there's potential, and we need to understand a little more how are these metals included. But in general, this topic is quite new. So this was, I think, the second or third thesis done in Chile related to tailings and considering how to reprocess this material. But I think, yes, it's possible.
Thank you. We have a final question by Akin. He asked if there are not enough economic mineable minerals in the tailings. How would you intend to manage the tailings sustainably without compromising the environment, environmental settlements like groundwater pollution?
Yeah, actually, there's one thing they were doing in the mine is using this as a building material. So they were taking this tailings and not considering this as an ore, but a raw material. So it's possible to cementate, I think is the accurate verb, the same galleries, because here they are using this Roman pillar system. So they are considering to to extract part of the pillars and fill it with tailings. That's one possibility.
Right, thank you.
Okay, thank you. So we can move, it's time, to the second talk of this session in mineral exploration. Our next speaker is Mariam Abbasian from Uppsala University, and he's gonna present results on T2D crook-lined reflection seismic imaging in the Zinkgruvan mine. I don't know if I pronounced that correctly, in central Sweden. So whenever you want.
Hello everyone, my name is Mariam Abbasian. I am a master student at Uppsala University, analyzing my master degree project. Here today I would like to talk about part of my master project that is entitled 2D crook-lined reflection seismic imaging in the Zinkgruvan mine, central Sweden. In this presentation, I would like to talk about the objective of the study, and then I would like to talk about the data acquisition and the methodology I applied to the data. Then I will discuss about the results, and then I will have some conclusions. The study area is in the Zinkgruvan mining area in the southern Bergslagen mineral district of central Sweden. The area holds over 30 million tons of massive sulfide mineralization, and is one of the 3 most prospective mineral districts in Sweden. The area, as you can see, is here in the map. And it has a very complex geological setting that makes the study area as a very challenging part. The objective of this study is to provide information applicable for near-surface structural imaging and how the mineralization continues at depths, and also a 3D visualization of the results will be presented, and then I will interpret them in connection with known geological observations and borehole data. Here is the survey profiles. Actually, the results presented here in this study were acquired as a part of a large scientific industrial research project in which 2D seismic reflection profiles were extracted from a sparse 3D data set and processed in a combination. And as you see, we have some survey profiles in gray that are related to that large project. But here I focus on 3 2D profiles that are named here as P1, P3, and P4. And as you can see, the red points are the shot positions, and here I will, in this particular presentation, I will just talk about the results considering this combined profile, that is a combined profile of P1 and P3. But actually, for the whole project, I did 3 different combinations of CDP lines for every 2 different profiles, which were processed to examine the 3D nature of the reflections. But here in this profile, I am showing how I did the CDP gathers. So it can be clear which part of this survey profiles I mean. So here I want to explain about the data acquisition in seismic reflection method. As you can see, it's a schematic figure that explains the instrumentation and the survey area in seismic surveys. This is a recording track, and this is a vibrator track that is introducing sound waves. It goes through the earth and back to the receivers that here are geophones and are recording in recording track and is monitoring there. So for our study, we used a 32-ton vibrator track. And we used both wired geophones as receivers and also wireless geophones that were recording the data. And here is the survey profile and the seismic vibrator and recording track. In this slide, I would like to talk about the processing steps I have applied to this data. And the main goal of this processing is to have a higher resolution and to enhance signal to noise ratio. To this end, I did a geometry setup that was application of field geometry, and then the whole processing is has been done in Claritas, which is a seismic reflection data processing software. Then I did a CMP sorting, which is an essential step before any further data processing. We need to have a shot receiver data be sorted based on the common midpoint gathers. That for this we select the traces with the same midpoints between receivers and sources. Then I did a first arrival picking automatically, and then I corrected them manually. Then a refraction and elevation static correction applied to remove the effects of near surface low velocity zone. And also the changes due to elevation, the changes due to the elevation, changing elevation of sources or receivers. And then a trace editing applied to remove all the noisy traces. And then I removed the 50 Hertz noise, and I did a bandstop filter at 50 Hertz. Then a bandpass filtering applied, and I did a normal automatic gain control with a 500 millisecond window. Then the first arrival energy removed, and I also did a residual statics, then a velocity analysis to have to choose the a stack velocity that best that is best for the data. Then I did an NMO correction, that is because to remove all the delays because of far offsets or the distance between receivers and shots. Then I did a stack, that is a final stack, and to line up all the reflection and to have a better resolution of the reflections. And also I did a post-stack migration to migrate all the reflections to their true depths. So here is an example of one of the shot gathers. This is a raw data, so I try to improve the resolution and to obtain a clear reflections here. So after doing a per-stack processing, I could enhance some reflections here. So as you see, maybe many of them are not visible here, but here you can see there is one reflection here, and also one of the biggest that is here. Also, there are some other features that I can mention that can be here or here. That seems to be reflections. Then, as a result, I did a stack. So here, by decreasing all the noises and improving signal to noise ratio, the reflections are highlighted. So here you can see the reflections, and here is the section of migrated data. You see how the reflections are more obvious here. So, and also I did a taper, that is because there was no valuable information here, so I just removed this part. By this, then this is a 3D visualize of the migrated section. So you can see see the profile, maybe here better. So this is the from this blue. It starts, and so here is the profile, and so it's beneath. These green lines are related to borehole data. So as you see, in some parts there are high amplitudes that shows that they are corresponding to the reflections that I have in my section. So this can be kind of, so it confirms the previous results. And also here I'm showing. So for the conclusion, through a number of tests and careful parameter selections, reflections in raw shot gathers were enhanced, and the final sections has show clear reflections associated with important geological settings. The results seem to be correspond to available borehole data from the site, and also the results can be used for future 3D reflection seismic surveys. And here I would like to show all the lovely field crew who acquired this data. And thank you for your attention. Any question?
Thank you, Mariam. So I think we have a question. Yes. From Bridge, which migration technique did you use? Slot, Kirchhoff? Was it constant velocity or variable velocity? In the result section, the vertical axis is in time or in depth?
It's in time.
So did you migrate? Which migration technique did you use?
Okay, sorry, may you repeat your question?
Yeah, that which migration technique did you use? and if you use a constant velocity for that or a variable velocity model.
It's actually I did a variable velocity model for that migration. Is that the answer?
Yes, and we have another question, the last one. Your processing flow did not include ground roll attenuation. Did you look into this, like for surface wave removal?
Yes, actually, I did a spherical divergence and also a deconvolution for that. That I actually didn't put in my final processing table, but I did, and I removed all the ground roll and I correct for them.
Okay, I guess it's time to move to the next talk.
Yes, the next talk is by Tatjana Pertus from Uppsala University, and she'll talk about broadband E5 and 5 seismic source and how it contributes to sustainable supply of raw materials.
Good afternoon, everybody. So I'm going to share my presentation now. So, okay, good afternoon, everybody. I'm going to talk about how does a broadband E5 seismic source contribute to the sustainable supply of raw materials. This study is based on the following objectives. The first one is to test the E5 broadband seismic source for hard rock and mineral exploration, where good mineralization and the good knowledge of mineralization is, and there is seismic data available. And additionally, we compare the data with other data sets from the same area. So our area of interest is the blood buried in Ludvika mine area. This belongs to the Bergslagen mineral district of south-central Sweden. Bergslagen is one of the most important mineral districts in the country, with a history of iron ore mining for several years. So here in this map, you can see that in white dots, we have we've displayed all the wearables available for the area. And in blue line, we have all the seismic data that was acquired for this study. Additionally, if we see the airborne magnetic map, what we can see is a very, very high anomalies in some of the areas, which is related with the mineralization of the zone. This mineralization in bloodberry consists of magnetite and hematite. The ore contains more than 50% of iron, dominantly from magnetite, but also hematite. So the source that we used for the acquisition was the E5 source with the following characteristics. First, the source is electrically driven. It is a vertical type vibrator with full drive frequency between 2 and 180 Hertz. Its weight is 1,650 kilograms, and the peak force is of 7 kilonewtons. And the design and dimensions enable it to be attached to locally available vehicles. It's one of the advantages of this source. Here I display some pictures. In the background, you can see the blood-buried mine, and in the left side of the picture, you can see the road that we used for the acquisition. In the figure A, you can see our source E5 in operation, and in the figure B, you can see the array that we use for the receivers. Those ones were 5 meters ahead from each other. So here you can see the amplitude spectrum for the receivers. These receivers were recording data with a natural frequency of 4.5 Hertz and 10 Hertz till 180 Hertz. So we use 425 receivers in cable system, 128 wireless receivers. With an interval receiver of 5 meters, we reached a maximum offset of 2,753 meters. The source is the E-Vibe source with a frequency of between 2 and 180 Hertz with a linear sweep rate. We use different sweep lengths, which were 14, 16, 18, and 20. The recording was still 3,000 microseconds with a sampling rate of 1 microsecond. The next step for this acquisition, it was the seismic processing. We use a conventional seismic workflow processing in which we took the FDU data and the wireless data, we merged it. On the right side of this slide, you can see one of the shots. This is a raw shot. And initially, we can observe that there are some reflections marked with red arrows. Those reflections are related to the iron deposits. After this, we apply some reflection statics. We did some QC. We applied some filtering. It was a bandpass filter and some spectral equalization, some AGC and residual statics. After this, we used an NMO correction. We did some stack, and then we continued to the processing for post-stack in the data. So we used some deconvolutions, the gap deconvolution and the FX deconvolution in order to remove multiples and to make the signal more coherent. So applied balance, and we did some velocity analysis. As a final step, we use some FK filtering, and finally we migrate. So all of this processing was aimed with in order to remove some noise and in order to remove some surface waves in order to have very clear the reflection of the iron deposits. So here you can see the migration of the seismic profile. This is a 2D seismic profile. So from the main reflection comes from the northwest till the southeast is the big one. This reflection is related to the mineralization. Beneath this reflection, there is another one which is related to iron deposit as well. So on the right side, which is the southeast till northwest, we have another reflection which is related to a fault. This fault was present since the beginning of the processing, and it was still remained till the end of the processing. Here on the left side, you see that we have some boreholes with some data available. And what we did, it was to compare these results with results of other seismic data that there was available in the area. So what we get, we have some known deposits in the area, which matches pretty well with the mineralization reflection from this 2D seismic profile. So now, the take-home message. So first is that there is a good quality reflection that is displayed even in the shot gathers and in the stack session. And this is due to the use of the E-Vibe as a source. We acquired data this data provide a good 2D image of the mineralization. Additionally, we obtain a cross-cutting reflection, which is present till the end of the processing. And with this, what we can see is that it's very important to have a control of the input variables in seismic work. In this case, as we did with the seismic source and all the seismic acquisition. And this allows to obtain good images and additionally to obtain good geological model for the area. Thank you so much.
Thank you, Tatjana. Are there any questions from the audience? Yes. Lavnish Gupta asks, how did you interpret the reflection as a fall?
This one. Well, this is something that we saw since the beginning of the processing, and it was maintained. It was remained in all the workflow. So additionally, with this, we compared this one with some seismic data from the area, 3D data, and that fault was still showing some reflections in that data, which make us to be sure about the reflection.
Okay, thank you. And as a follow-up on that same question, Clark answers, it appears that the fault is going to the surface, to the ground level. Did it show up on the surface?
Excuse me, can you repeat?
Clark, he asked, the fault, it appears in the section, it appears that it goes to the surface. And does it show up on the surface? Can you see it on the ground level?
Can you see in the what?
On the ground level, on the surface, does the fault reach the surface or not?
Well, this is still an open question for the project. So we projected this fault to the surface, and we have been working in this for 2D data and 3D data. So, but this fault came after the acquisition, so we still have to check if it comes from the surface.
Okay, thank you. And Didek asked if there was a comparison with other source survey of.
Sorry, you are mute. So Didek ask if you did any other comparison with other source or a vintage survey.
Yes, well, in this case, we have had some other data available with different source. This is the only one that was acquired with an eVive. So then we could compare the quality of the amplitude of the reflections. So yeah.
Yes, and we have an attendee that is raising his hand. Lori, I don't know how to give him permission to speak there. So.
All right, I just moved him to.
No, but he left, I think.
Nope,
so...
I moved him to a panelist position.
Oh, okay.
Let's see. Oh, here he is. So let me unmute him. He should be able to ask his question here in a second. For some reason, I can't unmute him, even though he's a panelist. So,
but he should be able to unmute himself or herself.
Yeah.
So,
yeah.
I don't know.
He should be able to.
Okay, is there any other question?
Maybe the person can write down the question.
Yes. but
Maybe he can enter it in the chat or the question and answer, since we can't unmute. Oh, looks like he left. All right. Oh,
okay, I guess we can move to, it's time to move to the next talk. So the final talk of this session is gonna be given by Shoshana Maris, also from Uppsala University, and she's gonna present cross-profile seismic data acquisition, imaging, and modeling of iron oxide deposit in the Blotberget mining area in south-central Sweden.
Hello, thank you. So I will present work in the same study area as Tatiana presented. I will present 2D seismic survey in this area with 2D processing, some reflection modeling, and a 3D visualization from these 2D seismic profiles, and some conclusions of the work. So as Tatiana mentioned before, this is in south-central Sweden, in Bergslagen, which is one of the most important mineral districts in Sweden. It has been important for centuries, and the mines in Blotberget, or Ludvika mines, as they are also known, they were active until the 1970s, and now new mining permits were granted, and the mining is planned to resume in the future. So that is why that is a lot of work that has been done in this area. So as it was shown before, this is the known mineralization. Oh, sorry. It is dipping southeast in sheet-like units at 35 to 45 degrees. Here you see some downhole logging data. It's showing magnetic susceptibility, and it's showing the mineralization found between 350 to 600 meters depth. You see here. And the host rocks that host the mineralization are metavolcanics. This mineralization is extending to at least 800 meters depth, known from boreholes, but from seismic data that was acquired before, we know that we interpret that it extends to more than 1,000 meters. So this seismic survey was acquired in 2016. It consisted of 2 lines, profile 1, profile 2. Here you have the main acquisition parameters. Profile 1 was about 2.2 kilometers long. Profile 2 was about 700 meters depth. The receivers were all 10 Hz geophones, partly cabled for profile 1 and connected to wireless sensors for profile 2. You see here some photos from the field with the receivers and the seismic source. The seismic source was a bobcat mounted drop hammer of 500 kilos. So as I said before, there has been work done at the site. There has been a seismic profile in 2016, and this profile was partly overlapping that profile from 2016. And this data were processed together. But in this 2016 survey, both profiles were active, so cross-profile recording was performed. So I will show you now. Some seismic data from these 4 data sets that were recorded. So you see here data along profile 1, along profile 2, shooting on profile 1 but recording on profile 2, and shooting on profile 2 but recording along profile 1. So all these data sets were processed individually and later merged. As you can see, the source provided good energy, and the first breaks are visible along the whole lines, even if the shots were at a distance. So these are the same shot gathers but processed. It's just basically a conventional processing flow for signal enhancement. And we notice here some reflections that are interpreted to originate from the mineralization, M1 and M2, possibly M3, and maybe an oppositely dipping reflection. Here you see R1. Here you see the stack sections from this profile. Profile 1, this was already published. Profile 2 turned out to be poor in reflectivity, not surprising due to the low fold and short line length. And you see here again the seismic profiles, but we should still make use of profile 2. And to start with, it is worth investigating if all these reflections that we see in the shot gathers are preserved in the stack sections, and if it's possible to see them in both seismic profiles. For this, I performed some reflection modeling work. Here you see another shot gather and the previous stack section. So I identified a couple of reflections in the shot gathers as well in the stack section, and I wanted to model them. This means that I assume a 3D planar structure. So I have a 3D geometry, a dip, a strike, and this is in a constant velocity medium, constant velocity for the background and for the reflector, and of course the density. These values are assumed from previous downhole logging data, and they are typical for hard rock environments. And the modeling assumes also the true geometry of the profiles. So when there is a match between the calculated travel times and the observed travel times in the shot gathers, we can assume that we found the correct geometry of the model of the reflectors. You see here the geometry of the reflectors. So reflectors M1 to M4 are interpreted as mineralization, while R1 and R2, oppositely dipping, are interpreted to represent structural features. The same modeling was performed also for profile 2, which was along the strike of the mineralization, but this profile, as I said before, did not show much reflectivity. Further, yeah, I forgot to say the modeling work assumes one reference point, and this was the beginning of the seismic line. And from here, we know the distance where the modeled reflectors would reach the surface. So this is performed in GOCAD, so there is some uncertainty, but the projection of the modeled reflectors still match some features on the geological surface map. This is the no mineralization here identified with M1, and it matches their modeled reflector as M1. Here you have M2, M3, and M4. So how they are interpreted here, M1 is a known mineralization, M2 and M3 possibly new mineralized horizons, and M4 we see here that it matches the lithological contact between the granite and volcanic rocks. Here you see the surfaces overlaid on the seismic section, and we see here that they match the reflection down to 300, 400, or 600 meters depth. These are the oppositely dipping reflectors, R1 and R2, and they again match here the surface lithological contact, and this projects further south to further south. And as Tatiana said before, one of these might be interpreted as a fault, but this is still work in progress. It's uncertain. And as I said before, the goal was to obtain a 3D image of the mineralization from these two profiles. So after each data set was processed separately in terms of pre-stack, then velocity analysis and residual static was applied, and here you can see the 3D cube along the inline and cross-line direction. This is the 3D geometry with 16 lines and 435 cross lines. So we interpret again M1 and M2, which better in the migrated section match the ore body pretty well, and the M3 and M4 are interpreted as new mineralized horizon. Also, they show a slightly different dip, and as well in the crossline direction. Here is another 3D visualization, and I will just take you through the 3D cube from inline 5 to inline 37, and you can see here how the reflections appear. Also, you see the cross lines, and you can see that they match very well the reflections from the inlines with the cross lines. So, of course, the cross line is pretty short, so it doesn't show the same continuity, and they also appear smeared due to the migration process. But as I said, they match the inline reflection. And this is just a snapshot of the same sections from inline 5 to inline 37. So basically, we can say that the 3D cube provides more reliable information about the depth of the reflection. And yes, sorry, I forgot to say that we can also estimate that we see about 300 meters lateral extent of the mineralization from inline 5 to inline 37. And we also interpret that there might be possibly new deposits. So this is a very interesting information. Also the oppositely dipping features that might provide very interesting data. And this study is encouraging for a future 3D seismic survey, of course. And thank you.
Thank you, Shershana. Are there any questions? Okay, we don't have yet in the questions and answers, and I don't think no one is raising their hands. No. So I have a question for you. You said, I think at the end, that the lateral extension, not like in the long line, but in the shorter line, it shows that the lateral extension of the mineralization can be of 300 meters. But do you think it can be more if you will have a longer line in the area?
Yes, it could be more. We just don't know more because the cross line stops there.
Yeah.
And also the boreholes are where we have borehole data, they're also concentrated along a small surface.
Okay, so we do have some questions now. The first one from Betayat. I want to just know about the static model, if it's a 2D or a 3D model.
The residual statics, it was on the 3D cube, so it's a 3D one.
Okay, thank you. Then we have another question from Clark. Oh, it was erased, so no more question. But we have another one from Didier. What is your binning interpolation method? 3D, 4D, 5D?
So I'm not sure I understand the question, but I think it's just 3D.
Yeah, the binning interpolation method, like I suppose you afterwards you use 3D, so it's referring to that.
So our 5-minute break is almost over, and welcome all back. My name is Afeli Ibrahimli, and now we are starting with our third section, which is dedicated to seismic application. Our first presenter in this section is Alexander Yablokov from Siberian Branch, Russian Academy of Science.
His topic is dedicated to data-driven approach to the inversion of surface wave data using machine learning techniques. So, Alexander, whenever you're ready.
Yes, thank you. Hello, colleagues. My name is Alexander Yapukov. I'm a researcher in Novosibirsk Institute and PhD student in Novosibirsk State University. And it is my topic presentation and part of my PhD research. And study object is multi-channel analysis surface wave. It's a seismology method, and multi-channel analysis surface wave is widely applied to investigate soil structure for geotechnical purpose. The multi-channel analysis surface wave contains the following steps. It's registration shot cases. And next is the spectral analysis and dispersion curve extracting. And final step is the dispersion curve inversion to estimate shear velocities models. In this presentation, we consider the last step of multi-channel analysis surface wave, it's the inversion. General methods for inversion of the surface waves are divided by local search methods, for example, Occam algorithm, and global search methods, for example, well-known Monte Carlo and recently proposed particle swarm optimization Gray-Wolf optimizer algorithm. Local search yields smooth shear velocity models mainly, whereas global search is computationally expensive. We proposed a new method, inversion based on application on artificial neural network. Proposed method consists of the 5 stages. On the first, we average all observed dispersion curves on survey area, and we give averaged dispersion curve. Next, we estimate the possible model range limits based on average observed curve. We give outputs thicknesses and shear wave velocities ranges. Next, we create training dataset. It means that we random picket models for our limits and calculated dispersion curves. Next, it is neural network training, and it's applicable for all dispersion curves for our observed area. Next, let's consider method in detail. Start from stage 2 because first step is a simple averaging, and for stage 4 we use algorithm proposed Cox and Tick, and we estimate the number of layers and depth variation range, that is thicknesses, from observed dispersion curve. Then we estimate velocity range by several steps, and as a result we got possible model limits from observed curve. On the next stage, we generate training dataset using uniform distribution for estimated ranges on the previous stage. Then we solve dispersion relation 500,000 times by numerical method using parallelization on CPU. We assumed this ratio for P wave, and we assumed raw density for constant. Thus, we got 500,000 models, and we got same amount of dispersion curve. On the final step, neural network is training and applied to data. Inputs for artificial neural network are dispersion curves, and outputs it is shear wave velocities and thicknesses. artificial neural network architecture includes 3 hidden layers. Neurons depends on frequencies numbers and layers numbers. Activation function is sigmoid, loss function is Canberra, optimization is Adam algorithm, and the validation dataset volume is 30%. After training, we can use INN waves to invert dispersion curves to 1D VS profiles. This slide presents distribution of mean absolute errors between the restored velocities and true velocities, and restored thicknesses and true thicknesses by pre-training INN for validation data. Validation data means data was not used for training. INN mean error is 50 meters per second for VS and 1.5 meters for thicknesses. Let's compare inversion results between proposed artificial neural network inversion and global search Monte Carlo algorithm and particle swarm optimization Gray-Wolf optimizer algorithm. As we can see, INN inversion provides results by model errors very similar to global search algorithms. Next, we conduct experiment to compare the computational times for considered algorithms. Hydrocarbon seismic exploration data are often several tens or 100,000 seismograms, and we suppose that we can always classify data to add 2-3 typical classes for the one survey area. For typical classes, dispersion curves are similar, and we can use same trained INN and computational time. Total computational time for artificial neural network presented in fourth column, and it is sum of the time of calculation curves, training, and application artificial neural network. Also, this calculation dispersion curves used for Monte Carlo inversion. Moreover, we use estimated models limits to PSO GWO algorithm, and we can see for a large number dispersion curves, for example, 10,000, artificial neural network is the fastest algorithm. It is especially important in the field of hydrocarbon seismic exploration, where surface wave analysis can be used to compute receiver static corrections for body wave processing. Now I will present field data processing. Data was obtained in Novosibirsk area, spectral analysis was performed, and dispersion curves was extracted. We have done inversion by artificial neural network and Monte Carlo and particle swarm optimization algorithm, and we use local search algorithm. It's a common version. We can compare presented results with Borehole stratigraphy presented in column, and artificial neural network and Monte Carlo results give best fit to borehole data. As a result, a new method for inversion of surface wave dispersion curves based on application of artificial neural network was proposed. Also, we suggest the data-driven estimating of the possible model parameter range. And our observation is that the accuracy of the proposed artificial neural network method is similar to that of the global search approaches. And artificial neural network inversion is faster than the global search algorithm when processing large amounts of data. It is tens of thousands short gathers. Thank you.
Okay, thank you, Alexander. Any questions? Not yet. So I have a question. You mentioned that you, as an input, use depth range and number of layers. Could you please tell how do you define these ranges and numbers? I mean, do you use seismic for that, or is it just randomly?
Okay, in this paper, Cox and Tick proposed algorithm based on the empirical parameters to estimate a number of layers and possible depth range. It's iteration method using empirical parameters, and we use its algorithm for estimate this range, and we also estimate shear wave velocities range by this short description. And if you want see in detail, I can send you this paper, and it's a use simple formula for estimate number of layers and thicknesses.
Okay, thank you. But how many iterations did it take to reach the desirable number? Like, was the process too long, or was it quite quickly?
For estimate layers numbers, you mean?
Yeah, for both.
We use one iteration because Cox and Tick use empirical parameter, and they use several values of these parameters, and they use iteration algorithm. But we show that in our research that artificial neural network not so depends for these empirical parameter, and we can use mean value of this parameter, and we use one iteration.
Okay, thank you.
So
there are also two questions. So the first one, how much noise the in an algorithm can handle? Did you check by putting some amount of noise to your raw data?
Yes, I skip this result, but we check our algorithm for when we add synthetic noise for dispersion curves, and we can see that artificial neural network not so influence for noise, and also our colleagues in Turkey, they first use artificial neural network. It was first paper, and they also check influence noise in the data for artificial neural network inversion. And neural network is not depends for not so depends for noise.
Okay, thank you. And another question, the training phase should be done every time that we analyze new data, or just once?
It's a good question. I aforementioned that when we processing large amount of data, we may classify data by several typical classes. For example, 10,000 seismograms, maybe more, and we can one times and for these classes, dispersion curves will typically very similar, and they will in this range, and we can use one limit range for one typical classes.
Okay,
For example,
thank you very much.
when we,
yes, yeah,
when
continue.
When we are processing data for very similar data or very small area, we get very similar dispersion curves, and they will in this and they will in our limits, and we can use one pre-trained ANN. But our research area will more different, maybe include permafrost or very contrast in velocities. Our dispersion curves will very different, and they may will in outside our diapasons, and in this case we should use new ranges and retrain our neural network.
Okay, thank you very much, Alexander. Yes, so our final talk will be given by Ivona Mika from EGH University of Science and Technology. And the topic is the analysis of mining geological conditions, influence on seismic activity in selected longwalls of Rudil Toqui coal mine.
Hello, can you hear me?
Yes.
Okay, so yeah, my name is Ivona, and I will present a part of my master thesis analysis regarding mining geological conditions influence on seismic activity in selected longwalls of Rudil coal mine. So this mine is located in Poland, in southern region called Upper Silesian Coal Basin. So the black box is the mine. You can see now the scale. And before I will begin with analysis description, I would like to explain the idea of longwall mining to those who are not familiar with it. So I will use two terms, longwall and a seam. So take a quick look on the left side. Longwalls that are marked with gray boxes and numbers from 1 to 9 are the places where the coal is extracted, and they can be compared to many corridors, but on the same floor in a house. So this floor or level is a seam, and they are visible on the right side. This is depth section. As you can see, the numbers of seams are not corresponding to the depth, but the higher the number, the bigger the depth. So let's now move deeper to better understand what I will be talking about. So as we are going deeper, you can see that the edges and levers on a map view on the left seems to overlay. This one is pretty well organized. More problems will occur with chaotic excavation when, for example, edges are perpendicular. Some general information about this mine. So you can see on the left side on a 3D model of one of the seams that this is in syncline axis, and the scale is pretty big, so I will focus in the presentation only on selected longwalls from the map that is on the right. And before this topic that I'm now touching, the previous analysis was realized with various seismological approaches, but I will mention only one conclusion from them. that the spatial location inaccuracy was so significant that it was necessary to check correlation that I am now showing with time, not with the surface. So I will now show the main part, how the released energy from earthquakes that were peaked on specific long walls can be correlated with presence of adjacent seams edges. What's even the purpose? This mine is not well known yet, that's for sure, but moreover, the mining there is under hampered conditions. So not only the seams edges, but also a thick brittle sandstone above that many earthquakes are correlated with. And the second purpose is that geomechanics in that mine company that I have the data from are saying that adjacent seams that are more than 150 or 2 meters above long wall don't have influence on the energy and occurring of earthquakes. My observations and some experts that I was consulting with, there is an impact of these edges, even more than 200 meters above, and I am trying to prove it in this presentation. And the last one, minimizing of seismic hazard in coal mines is always very important. So every analysis that will prevent some damages, rock bursts or even deaths is helpful. So right now I will show what is the processing sequence. First for energy. You can see the long wall that I will be talking to. It's highlighted now. And first I divided it into intervals of 15 meters. And then, as I said before, I took time boundaries, not spatial. So this box, blue box that you can see now, results from time period, and the earthquakes, the seismic energy released in these earthquakes was added in between specific dates, not between this region spatially. And then I performed moving average on interval of 45 meters and a second one on interval of 75 meters because the variations of energy here are very strong and very fast. Later on, I decided to create a brand new parameter called SED, seam edges distance, because I wanted the interpretation to be objective, and I wanted to have the same approach for every long wall, not to change it to better suit the data. So there were two factors that had an impact on SED value. It was horizontal and vertical distance to the edge of adjacent seam. As you can see in the table on the right side, with the increase of vertical distance, the SED value was decreasing. I also took into consideration faults that were noticed in the long wall. And the figure on the left shows you where spatially I located the minimum with the blue one and the maximum with the red line. So I started to, the minimum starts 10 meters before the edge and continues to 10 meters after it. And the maximum starts 30 meters from the edge and continues to 50 meters. To show you that the situation from the beginning was very perfect and not so real, here is the long wall that I am talking to. It's highlighted. And right now I will highlight some seam edges that are above it, and they are more than 200 meters away. So here's the first one, second one, and the third one. The fourth one is not highlighted. Right now I will just go through the examples of results from one long wall before I will start a very quick explanation of the graph. At the top, you can see the distribution of mean total energy, so the energy that was added and later on averaged. The bottom axis is the long wall advance. And at the bottom, you can see the map almost the same as here, just made on the purpose of MATLAB, where you can see with the red box the long wall that we are talking about, and with other lines the edges that are above. And in the middle, there is a parameter that I created called SED. The continuous line is a smooth version, and the dotted line is a version only after 3-point filter. This gray box will indicate the phase, the phase of the long wall, so the long wall advance. So the extraction of coal will go from the right to the left. So let's go forward. We can see that this edge corresponds to the minimum, both on energy and on my parameter. And 30 meters away from that, we have maximum, both on each distribution. So I will show just a few examples and go through it. Second of all, we have a circle here and edges, minimum again, and maximum. This one is the first imperfection on the distribution. Because the situation is complicated, you can see that there are more edges that also have an influence on that part. So let's move forward. We have next edge, minimum, that is a little slightly more on the left on the SED than on the energy. And again, the maximum is in the same place. Right now, here is the fault, and it also have an impact. This section I will not talk about because it's a variation in the fault. And here are the more, again, maximum, minimum with just above the edge, maximum, and the same situation here at the edge. Here are the two edges. I just took into consideration the effect of superposition, so it was added. For me, the visual correlation is quite good. Of course, there are some imperfections, but there are more conditions, more factors that influence release total energy than only edges that are above the long wall. So just a quick another example to show you more simplified version. The left side is not explained because the edges are very chaotic and it will be very hard to right now distinguish it in a short presentation. So as you can see, the edges are not even only just above the long wall. They are also slightly on the right and slightly on the left. And they still have an impact, in my opinion. The first bump is not so quite visible, but the second, the third, and the fourth one are pretty in the same place. And I think that it also proves my hypothesis that the edges have an impact on released total energy. So again, on earthquakes that occur in the data set. So what are conclusions? Just to repeat, the correlation is visible, in my opinion, of course. The impact of the edges is even not only directly above long wall, but also when they are slightly on the right on the left side. And there is a need to perform more statistical evaluation and work on SED values, because as you can see, they are not corresponding to the values of energy. So this is a work to do about it. So thank you for your attention.
Thank you very much. Regarding the questions, we have the question. So why do you think the SED parameter does not fit total energy in the middle of the graph? I mean, in the middle of the long wall advance.
Okay.
So I guess that's the slide that you showed previously.
Okay, I can see it now. Because I am missing one maximum there. If I would take into consideration that the fault here is it's dividing into two separate faults exactly in that place, but I decided not to rely on that only. And yeah, I think that there is one maximum missing above that X, slightly on the left of that X. You can see it here. I thought it's that.
Okay. Thank you. So there is a compliment to you. Great job, Ivana, from Roman.
Thank you, Roman.
I also have a question. Do you somehow tackle the problem of these spatial locations in your work? I mean, yeah. Go ahead.
Okay, I tried, but these peaks are not mine. They are performed by mine seismologists, and obviously they have so many earthquakes every day that it's hard to do it perfectly. And even they told me that it's impossible to rely on it because they are a little bit random. I tried to make any analysis from that, but it actually doesn't make any sense. So I cannot fix it because I'm not in the station on the mine. So I have only catalog and maps. So I cannot do anything about it right now. I could repeat every earthquake, but it's tens of thousands of earthquakes. So it doesn't make sense right now.
Okay, thank you. But like how the impact of this horizontal and vertical distance can be minimized to these SED values?
I think that the impact cannot be minimized, but the mine can be aware that there is a problem exactly in that place, and they can be more aware, then they can be more secure and prepare for that. There can be a rock burst, because in that place, like 2 long walls away from the one that I'm showing now, last year there was a strong rock burst, 1 person died, and it was just in the area of these edges. So just to be aware that there is a problem and you have to take care and slow down the excavation.
Okay, thank you very much, Ivana. So I will give word to Aurelian.
There are no further questions. Then we're coming to the wrap-up and closing remarks. I want to give a big thank you to all of our speakers today. You gave great presentations and interesting insight in your topics. I hope that you also enjoyed your presentations, that you were happy with the questions and comments from the audience. I want to thank the audience, of course. I can say that we had up to 3, even 4 times as many people in attendance than for the first event, which is a big success. We hope that you also enjoyed the talks, that you learned something, and we hope that we can welcome you for the 3rd edition, either again as an attendee or maybe even as a speaker if you're still a student then. You're welcome to hand in your abstracts. And I want to give a big thank you to all of our session chairs and the people in the background, to Laurie, to Stephanie, to Mariana, who all of them helped to organize this event. It was a lot of work, but I think everybody enjoyed it, and we are very happy to have this again.